Even if I'm not, am I audible? Can anyone just let me know whether I'm audible?
Am I audible now? Hello. Hello. Am I audible? Okay. So, wait a second. So, first of all, thank you so much for joining, even after this last moment change in time schedule. From next week, we'll be having on the same time. Okay. Is it recording? So, I hope you all have been through the lecture videos. Today, we'll be solving some problems related to the Hahn Banach theorem. So, this is our tutorial. Tutorial 4. Question number 1. Show that L2 is strictly convex and L1 is not. So let's just recall what do we mean by convex Banach space. Recall. A non-linear space X is said to be strictly convex if for every x not equal to y with norm x equal to norm y equal to 1, we have norm tx plus 1 minus ty strictly less than 1 for every t in 0 to 1. That means if there are 2 points x and y in the norm linear space such that their norm is 1, suppose this is some space, these are 2 points with unit norm, then the points lying on this line joining x and y, all these points must have norm strictly less than 1. So less than equal to 1 is clear due to the triangles inequality. Clearly, we have this norm tx plus 1 minus ty is, screen is not visible. Oh, wait a second. I think I forgot to share. So is it visible now? Can you see my screen now? Okay. So let me recall it again. So we need our first question is we need to show that L2 is a strictly convex space whereas L1 is not. So what do we mean by convex space? Strictly convex space. For strictly convex spaces, if x and y are two vectors with unit norm, then all the vectors lying on the line joining x and y must have norm strictly less than 1. So less than equal to 1 is directly clear because of the triangles inequality. We have something of this form. Now since norm x and y is equal to 1, this is basically 1. So less than equal to is always there for any norm. If we have strict inequality, in that case we say that this space is strictly convex. So we need to show that L1 is not convex whereas L2 is strictly convex. So let's start with L1. We need to show that L1 is not convex. That means if we can find an example of function of vectors x and y in L1 such that for some t tx norm of tx plus 1 minus ty is equal to 1, in that case we'll get contradiction because anyways it cannot exceed 1, and if it is strictly less than 1 then again then we don't, that is not what we want. No, we need to show that L1 is not strictly convex. So for that, let x be the sequence with first term 1, rest of the term 0. Clearly it belongs to L1, and its norm, L1 norm is 1. Similarly, taking y to be the sequence with second term as 1, rest of the term 0. Again, this will belong to L1 and norm y is 1. Now, what can we say about norm of tx plus 1 minus ty? L1 norm. Firstly, let's see how the sequence will look like. So, its first term will be t, then second term will be 1 minus t, and rest of the terms will be 0. L1 norm. And what is our L1 norm? This is summation I from 1 to infinity. Or we can write it directly. In this case, this will be mod t plus mod 1 minus t plus 0, 0, 0. Now, since for 0 less than t less than 1, this is equal to t plus 1 minus t, because obviously t is less than 1, so modulus 1 minus t is 1 minus t itself, so this is equal to 1. Hence we got an example of of two vectors x and y in L1 such that norm x is 1, norm y is also 1, but the vectors lying on the line, in fact all the vectors lying on the line joining x and y have norm equal to 1. Therefore, L1 is not strictly convex. Is it fine? So let's move to the space L2. For L2, we claim that L2 is strictly convex. Now let u not equal to v, sorry, u and v belongs to L2 are such that their norm are equal to 1. So can you tell me whether these vectors can be linearly dependent? Can anyone tell me whether these vectors will be linearly independent or dependent? So they can never be linearly dependent, because suppose if u and v are linearly dependent, yeah, they will be always linearly independent. Then there exists some alpha in R. Let us field is R, no? Alpha in R such that we have u is equal to alpha v, and in that case norm u, and obviously this if they are equal, in that case so we have to take the such that this and this and u not equal to v, no? So since uh, u is not equal to v, alpha should be not equal to 1. This is equal to modulus alpha times norm v, which is mod alpha. But we know that norm u is equal to 1, which is not equal to mod alpha. Now this gives us a contradiction. Therefore, there should be always linearly independent. This implies the set u comma v is linearly independent. We'll be using this fact. So now, what can we say about L2 norm of tu plus 1 minus t v square? This is equal to summation I from 1 to infinity tui plus 1 minus t vi square. Now this is equal to summation I from 1 to infinity t square ui square plus 1 minus t vi square plus 2t 1 minus t ui vi. So we can just split this sum. Let's write it in the next step. This is equal to t square times L2 norm of u square plus 1 minus t times L2 norm of v square plus 2t 1 minus t times the inner product ui vi. Now this will be strictly less than t square plus 1 minus t square plus 2t 1 minus t norm u norm v. We are getting this strict inequality because in the Cauchy-Schwarz inequality we know that we have equality if and only if the functions, the vectors are linearly dependent. Now since the vectors are linearly independent, we have this inequality. This is because u and v are linearly independent, and this is by Cauchy-Schwarz inequality. Now this, since norm u and norm v are equal to 1, so this is equal to t plus 1 minus t whole square, which is basically 1. This gives us norm tx plus 1 minus t, sorry, it's u, norm tu minus v2 is strictly less than 1. That is what we wanted. Since uv belonging to L2 such that u not equal to v and norm u equal to 1 equals to norm v are arbitrary, we get L2 strictly convex. So is this proof fine with everyone? In order to show that L1 is not strictly convex, we searched for an example, and and to prove that L2 is strictly convex, we have mainly used the fact that the equality in the Cauchy-Schwarz inequality is only if and only if the vectors are linearly dependent. And in our case, the type of vectors that we need to take because for the definition of convexity, strictly convexity, the vectors must be linearly independent. So that gives us the strict inequality. So is it fine? Well, let's move to next question. Next question will be using this convexity of strictly convexity of L2 space. Question number 2. Let V is equal to L2. W is set of all those x in L2 such that their second term, sorry, even terms are 0 for every I in N, where x is of the form xi, so xj, j from 1 to infinity. Let f from W to R be a continuous linear functional then its Hahn Banach extension is unique. So what do we mean by the Hahn Banach extension? Suppose f is a functional from W to R. W is a subspace of V. Then G from V to R is said to be the Hahn Banach extension of f if G restricted to W is equal to f and operator norm of G is equal to operator norm of f. Now we need to show that there exists unique Hahn Banach extension for a functional f defined on this subspace W of the space VL2. Okay. Summation. Now let if possible, there exist G1 and G2 from V means L2 to R such that norm G1 is equal to norm F is equal to norm G2 and G1 restricted to W is equal to F is equal to G2 restricted to W. Now let capital G1 is equal to G1 by norm F, just scalar multiplication by 1 by norm F. We are taking without loss of generality, let F is non-zero. Therefore, norm F is non-zero and hence this G1 is well defined. Similarly, G2 as G2 by norm F. This implies norm G1 is equal to 1 is equal to norm G2. Now G1 and G2 are elements in, now see, G1 and G2 are linear functionals defined on the space L2. So G1 and G2 are from L2 to R. That means G1 and G2 belongs to the dual space of L2. And by Rees representation theorem, we know that for every functional f in L2 star, there exists some Vf in L2 such that f at u is the inner product of U with F, VF for every U in L2. Or we can say directly that, which implies that this the dual space of L2 is equal to L2. Now we will use the convexity of the space L2, strictly convexity. Now, since L2 is strictly convex and L2 star is equal to L2, we get norm G1 1 by 2 plus 1 by 2 G2. This should be strictly less than 1. That means norm G1 plus G2 is strictly less than 2, which implies norm G1 plus G2. Now this is equal to, see, small g1 is basically scalar multiplication of capital G1 by norm F. So this is norm F G1 plus norm F G2, which is equal to norm F norm G1 plus G2. Now this is strictly less than 2 times norm F. Okay. Also, let's mark this as equation first. Also, norm G1 plus G2, this is equal to supremum mod G1x plus G2x, where this x is in L2 with norm less equal to 1. Now this should be obviously greater than equal to supremum of mod G1x plus G2x, where x belongs to W, because W is a subspace of L2, with norm x 2 equals to 1. Now this one can easily see, because norm G1 and norm G2 are equal to norm F, this can be written as greater than equal to 2 times norm F. Or in fact, this will be equal to 2 times norm F. Now this gives us a contradiction, because in equation first we have seen that norm G1 plus G2 is strictly less than 2 times norm F. But from here, from equation 2, we get a contradiction. Therefore, by contradiction, we have, what do we have? Unique extension. We can, the Hahn Banach extension is unique. So is it fine? If you have any doubt in any step, please let me know. So mainly we started with an assumption that suppose there exists two distinct extensions. Uh, in that case, both will the norm of both the functionals will be equal to norm of f. Using that, we constructed two linear functionals, capital G1 and capital G2 with norm 1, and then using the strictly convexity of space L2 and the fact that the dual space of L2 is L2 itself, we got this kind of strict inequality, which gave us that norm G1 plus G2 is strictly less than 2 times norm F. But in fact, since W is a subspace of L2, from there we get that norm G1 plus G2 should be greater than equal to 2 times. Basically, it should be greater than equal to norm G1 plus greater than equal to 2 times norm F. So therefore, the extension in L2, the Hahn Banach extension on L2 is unique. In fact, since L1 is not strictly convex, you can try to find different extensions. That means in the case of L1, this Hahn Banach extension is not unique. Okay, let's move to next question. Number 3. Prove the analytic Hahn Banach theorem using the geometric version. So let's firstly recall what do we mean by the geometric version and the analytic version. So the version that we had used earlier, this one is basically the analytic one. So I'll just recall it. Geometric Hahn Banach. It states that if X is in V, suppose let's start with the norm-linear space. Let V be a norm-linear space. X belongs to X is a vector in V, and U is an open and convex set with X not belonging to the set U, then there exists some functional f defined on V star such that fx is greater than all the images of elements in U for every U in U. That means if we have an open and convex set and a point which is far away from that set, in that then we can find a functional for which the values at point the value at point outside this open and convex set is strictly greater than the images of the points in images of all the points in this set U. And then comes the analytic version. So in the analytic version, we can find an extension. Let W be a subspace of V and F from W to R is a continuous linear function. Then there exists a functional G defined on V to R such that G restricted to W is equal to F and norm G is equal to norm F. So here we need to prove the analytic version using the geometric one. I hope you all must have seen in the lecture videos there they have the faculty has proved how we can prove the geometric version using the analytic version of the Hahn Banach theorem. So this time we'll be seeing its converse part. So in order to prove the analytic, we'll first start with a subspace and take a functional f defined on the subspace. Then we'll search for its extension such that its norm is also equal to the norm of functional f. Let W be a subspace of V and f from W to R is a continuous linear functional. Now suppose if norm f is equal to 0, then clearly f is trivially equal to 0, and in that case taking g from V to R, gv is equal to 0 will suffice our requirement, and hence we will be done. Now case 2, when f norm f is non-zero. So in order to use the geometric version, clearly we need to have some set open and convex set U. So let's start with that. Let W tilde be the kernel of function f. We all know that kernel of the linear transformation is always a subspace of the domain, and let B01 be the open unit ball in V. Then one can easily check that then by openness and convexity of B01, we can see that U is equal to W tilde plus B01, which has the elements of the form small w tilde plus U, where W tilde belongs to W tilde and U belongs to B01, is open and convex. Now we need to find some vector in W so that it is away from U, and hence we can apply the geometric version of the Hahn Banach theorem. So let W belonging to W be such that f of W is equal to norm f. Clearly we can find such W, we can find such W because if suppose alpha is equal to some fx which is non-zero, obviously since our functional is non-zero, we can find some x such that its image is non-zero. In that case, f of norm f times x by alpha, I have just scalar multiplied x by norm f by alpha, this is equal to norm f by alpha times fx, because f is a linear transformation, which is equal to norm f. Therefore we can find such W. So instead of writing it complexly in the form norm f x by alpha, I take it to be W. Then I claim that then this W should not belong to U. So I think this should be V because W is a okay. Okay. This is W. Now I claim that W does not belong to U. Now suppose if W belongs to U, now what is U? U is W tilde plus B01. This implies W is equal to some W tilde plus some U where norm U is strictly less than 1. In that case, FW will be fw tilde plus fu by since f is linear, and this is equal to fu. Why? Because w tilde belongs to capital W tilde, which is kernel of f, and we all know that kernel f, that's the definition of kernel f. Now every element in kernel f is mapped to 0. This gives us fw is equal to fu. This implies mod fu fw is equal to mod fu, which is less than equal to norm f times norm u. Now since u is in B01, norm u is strictly less than 1. So this is strictly less than norm f. This gives us mod fw is strictly less than norm f. But we had taken w such that fw is equal to norm f. So, but mod fw should be equal to norm f. Now this gives us a contradiction, and hence w is not in u. Therefore, this u is the open convex set, and this w is an element in w which is away from u. Therefore, we can find this w should be in v. Yes, this w should be in v. Of course, when w is in w, then it will be in v as well, because w is a subset of v. No? Then by the geometric version of the Hahn Banach theorem, we can find a linear functional. Then by geometric Hahn Banach, we can find a functional lambda. We can find a functional lambda in v star such that lambda w is strictly greater than lambda u for every u in u. Now this lambda will help us to find the extension. Now since 0 is in u, this implies lambda w is strictly greater than lambda 0, and since lambda is a linear transformation, it maps 0 to 0. This implies lambda w is strictly positive. If I take this lambda w to be equal to alpha, we have alpha strictly positive. Now I define lambda bar from V to R such that lambda bar at any point u is just norm f by alpha times lambda u for every u in V. Now this lambda bar we will see that this lambda bar will be the required extension. Let's see how. This implies lambda bar at w is equal to norm f by alpha lambda w. Lambda w is alpha, so this is norm f. Therefore, lambda bar at w is equal to norm f. Now since B01 is a subset of u because 0 belongs to w tilde, 0 plus u belongs to u for every u in B01. Okay. That means for every element, this implies for every u in B01 from this star, let me mark this as star, by star lambda w is strictly greater than lambda u by star. Okay, so this gives us lambda bar at u, which is equal to norm f by alpha times lambda u. And since norm f and alpha both are positive, I can write it strictly less than norm f by alpha lambda w, which is equal to lambda bar at w, and we know that this is equal to norm f. This implies lambda bar u is strictly less than norm f for every u in B01. This implies, by the definition of operator norm of lambda, u is equal to, sorry, not u, operator norm of lambda is equal to supremum modulus lambda bar u, such that norm u is strictly less than 1. This is strictly less than norm f, less than equal to, because we have supremum. So this implies lambda bar norm is less than equal to norm f. So as I said, we will be showing that this lambda bar is actually the required extension. We'll be showing that lambda bar restricted to w is actually equal to f, and the other side of inequality as well. That means norm of lambda bar is greater than equal to norm f. And in that case, we will be done. Let me mark this as equation. Okay, star. We haven't given any number, so I'll mark this as equation 1. Okay. Now we have W tilde is a subset of kernel lambda bar. I can say this because suppose there exists some W tilde in W tilde minus kernel lambda bar, that would imply that lambda bar W tilde is non-zero. Then we can find some real number t such that lambda bar t w tilde is, which is equal to t times lambda bar w tilde. Now since lambda bar w tilde is a constant, I can make t large enough so that this is strictly greater than norm f. Because norm f is a constant, I can take t large enough so that I get this inequality. Now this norm f is equal to lambda bar w. We have seen earlier lambda bar w is equal to norm f. This gives us lambda bar t w tilde is strictly greater than lambda bar w. But since w tilde is in w tilde, which is a subset of u, implies t w tilde belongs to w tilde, because w tilde is a subspace. It is the kernel space. No? This is again a subset of u. And we know that for every element, for every vector in u, lambda bar u is strictly less than lambda bar w. We had seen this using the Hahn Banach theorem. So this gives us that w tilde must be subset of kernel lambda bar. Now, for any w, we have taken w specific, w bar belonging to capital W, we have f of w bar minus f w bar by f w times w is equal to, and this is f w bar minus, now since these are just scalars, they will come out, minus fw bar by fw times fw. This is equal to 0. This implies w bar, sorry, this is not f, this is lambda. So this is lambda bar, lambda bar, lambda bar, lambda bar w. Now we have seen this is in kernel F, kernel F. Okay. This is F only. This is F, fw bar minus fw bar by fw times fw. This is 0. This implies w bar minus fw bar by fw times w belongs to kernel F. Now kernel F was w tilde, and this is a subset of kernel lambda bar. This is a subset of kernel lambda bar. This implies w bar minus fw bar by fw times w belongs to kernel of lambda bar. This gives us lambda bar w bar minus fw bar by fw times w is equal to 0. This gives us lambda bar w bar is equal to fw bar by fw times lambda bar w. Now see lambda bar w is equal to norm f and fw. Initially we had taken w such that fw is equal to norm f. That means fw and lambda bar w both are equal to norm f. Hence we can just cancel them. This is norm f by norm f. These gets cancelled out. This is equal to fw bar. Now we had taken w bar, an element of w arbitrarily, and we got, therefore lambda bar w bar is equal to fw bar for every w bar in w. That means lambda bar restricted to w is equal to f. This is what we wanted. We wanted to show that this lambda bar is the extension of f. So its restriction over w is equal to f. Now what we are left with, the other side of inequality. Now clearly, since w is a subspace of V, we will get the other side. See, norm lambda bar is supremum mod lambda bar x, where x is in w. This is obviously greater than equal to supremum mod lambda bar. Sorry, this is in V, mod bar x in w, because w is a subset of V, and this is equal to, now on w, lambda bar is equal to f, and this is the, sorry, this is upon norm x minus 0, this is upon norm x minus 0, this is upon norm x minus 0, and this is the definition of norm f. This gives us norm lambda bar greater than equal to norm f. Hence norm f is equal to norm lambda bar, and lambda bar restricted to W is f. Therefore, we got the extension. So let's recall what we did. We started, firstly we have seen that for if the function is 0, then trivially the 0 function will suffice the requirement, will be the required extension. For non-zero f, we started with taking w tilde to be its kernel, and using that kernel and the unit ball in V, we constructed an open and convex set. Then in order to then we searched for an element which is outside or away from this open and convex set. For that, we had taken some point w such that fw is equal to norm f. Clearly we can find this such a w, and we have seen that this w will surely not belong to the set u, and hence by the geometric version of Hahn Banach theorem, we found a linear functional lambda such that lambda w is strictly greater than lambda u for every u in this open and convex set. Now since u is just w tilde plus some unit plus a unit ball, therefore 0 belongs to this set u, which gave us that which tells us that lambda w is strictly positive, taking that lambda w to be equal to alpha, because w is fixed for now. So this alpha is fixed, and using this alpha I constructed a linear functional lambda bar, which again at point lambda at point w gives the value norm f. So at w, this f is also equal to norm f, lambda bar is also equal to norm f. Now this lambda bar uh, turns out to be our required extension. So if there is any doubt in any step, please let me know. I would like you to go through the proof again, please. I'll wait for 5 minutes. Please go through it. Okay, then let's move to next question. Question number 4. Consider the natural map. So by natural map, we mean the evaluation map. I'll explain how it is defined. Map J from V to V star star, where V is a Banach space. Let B and B star star be the unit balls in V and V star star respectively. show that JB is dense in B star star if and only if V is reflexive. So in order to solve this problem, one should be aware of the terms dense. What do we mean by dense in B star? And what do we mean by reflexive? So we need to show, we say that JB is dense in B star star if JB closure is equal to B star star. That means for any vector V in B star star, I can find a sequence, can find a sequence UN in B such that JUN converges to V in this space V star star. So V star star is basically the dual of the dual space. So if I'm saying that V is an element in V star star, that means V is a functional defined on V star to R. Okay. Then comes the reflexivity. We say V is said to be reflexive if the natural or the evaluation map J from V to V star star, where JV is equal to TV for every V in V, and this TV, since it is an element in V star star, this should be a functional, linear functional from V star to R. And for this evaluation map, this TV is defined as TV of F is the value of F at V for every F in V star. Now, if this natural map is surjective, then we say the vector space V is reflexive. That means for any vector, for any linear transformation, linear functional on in V star star, there should exist some vector V in V such that this functional is basically equals to TV. It is some evaluation map. That means all the functionals in V star star are actually the evaluation maps. So in that case, we say that the vector space is reflexive. So now we need to show that this set JB is dense in B star star if and only if V is reflexive. So let's see its solution. For some, let's start with a fixed V. Now fix a V, fix some V in V. This implies TV, which is equal to the image of V, belongs to V star star. That means again TV is from V star to R, where TVF is equal to F at V for every V in. So instead of V, I should write something else. No, it's V, F at V for every f in V star. Now mod TVF is equal to modulus FV. Now this is less than equal to norm F, norm V, because F is a linear functional, for every F in V star. That is, we have norm TVF is less than equal to norm V times norm F for every F in V star. This implies, by the definition of operator norm, norm TV is less than equal to norm F. Now, if we could find some specific functional F in V star such that TV is equal to norm F, in that case, our norm TV is equal will be equal to norm F. Now, if you remember, using the Hahn Banach theorem, there was some corollaries and results based on the Hahn Banach theorem. We can find by the analytic Hahn Banach theorem, we can find a functional f in V star such that f at this point V is equal to norm V and norm F is equal to, this was one of the corollaries of the analytic Hahn Banach theorem, and for this F and norm TVF is equal to norm FV, this is equal to norm V. Therefore, this upper bound is attained at this F. Therefore, norm TV is equal to norm V. Now this tells us norm JV is equal to norm V. That means this function J is an isometry. And we know that isometry is 1, 1. Instead, I should write. Now, since V belonging to V was arbitrarily fixed, we have norm JV is equal to norm V for every V in V. This implies isometry. Now let's start with one side. Now suppose V is reflexive. Then by the definition of reflexivity, we have this J is surjective. This gives us that J is a bijective isometry. In that case, I say that JB should be equal to B star star, because if I take, suppose I take some functional T in B star star, for B star star, since J is surjective, there exists some V in V such that JV is equal to T, since J is onto, and norm V will be equal to norm JV, which is equal to norm T. Now since T is in B star star, which is the unit ball in V star star, so this is less than equal to 1. This implies norm V is less than equal to 1. V belongs to B. This implies T is equal to JV belongs to JB. This gives us B star star is a subset of JB. Similarly, on the other side, if I start with some element in JB, suppose TV belongs to JB, in that case, this TV is basically JV, then norm V is equal to norm JV. So we need to show that for T in JB, TV in JB, it should be in B star star. So it's norm. So this implies norm TV is equal to norm JV, which is equal to norm V is less than equal to 1 because V is in B. This implies TV is in B star star, which gives us JB is a subset of B star star, and hence JB is equal to B star star. This implies we need to show that JB is dense in B star star, so JB closure is equal to B star star closure, which is basically B star star itself because it's the closed unit ball. Therefore, JB is dense in B star star. Means reflexivity of V gives us that JB is dense in B star star. I hope this one side of the proof was fine with everyone. We have mainly used the definition of reflexivity, proved the fact that this functional J will be an isometry, and this fact that this J is isometry helped us to prove that JB is dense in B star star. Okay, so let's move to the converse part. Conversely, we need to show that if JB is dense in B star star, then V should be reflexive. That means this function J should be surjective map. Conversely, let JB be tens in B star star. Now let W belongs to B star star be arbitrary. Now since JB is since JB closure is equal to B star star, this implies there exists a sequence. We can find a sequence in JB. So since the sequence is in JB, I can write it of the form TVN in JB such that this TVN converges to W as n tends to infinity. Here these Vn belongs to B for every n in n. Now this implies, we all know that convergent sequence is always Cauchy. This implies TVN is a Cauchy sequence in V star star. V star star. This implies norm TVN minus TVM V star star goes to 0 as n tends to infinity. Or we can say that norm JVN minus JVM V star star goes to 0 as n and m tends to infinity. Now since J is an isometry, this implies norm Vn minus Vm norm of V is equal to norm J Vn minus JVM norm in V star star goes to 0 as n and m tends to infinity. This implies Vn is a Cauchy sequence in Vn is Cauchy in V. And we also know that norm Vn is less than equal to 1 for every n in n, because Vn belongs to this set B. Now since V is a Banach space, we were given that V is a Banach space. That means Cauchy sequence must be convergent. Since V is a Banach space, we have V is a Banach space. Vn must converge to some V in V, and norm V should be equal to limit n tending to infinity. Norm Vn should be less than equal to 1. This implies V is in B and norm Vn minus V tends to 0 as n tends to infinity. Again, by the fact that J is an isometry, this implies TVN minus TV, which is equal to norm JVN minus JV, which is equal to norm Vn minus V goes to 0 as n tends to infinity. This implies this TVN converges to TV. But originally we had taken that we had the fact that TV converges through this W in B star star. So by uniqueness of limit, TV is equal to W. So by uniqueness of limit, Tw should be equal to Tv. Now this Tv is actually Jv, where this V belongs to B, that means this belongs to JB, because V belongs to B. Now we had taken W, an element in B star star. It turned out that it is an element in JB. This implies B star star is a subset of JB. And if I take an element in JB and if TV belongs to JB, then norm V norm TV, then norm TV, which is equal to norm JV, is equal to norm V. Now this norm V is obviously less than equal to 1 because TV is in JB, that this V is in B, so this norm is less than equal to 1. This implies this TV belongs to B star star, which implies that JB is a subset of B star star. Hence, JB is equal to B star star. Now we had to show that this J is actually surjective. That means for any element F in V star star, I can find some vector V in V such that J of V is equal to that F. I will use the fact that JB is equal to B star star to prove this. Now let F belonging to V star star be arbitrary. Without loss of generality, let F is non-zero, because clearly 0 is mapped to 0 and we don't need to look for its pre-image. This implies F by norm F belongs to B star star, clearly because its norm is actually equal to 1, so this belongs to B star star, now which is equal to JB. This implies there exists some V in B such that F by norm F is equal to JV. This implies F is equal to norm F times JV. Now since norm F is just a scalar, I can take it inside. This is equal to J norm F V. Therefore, for every F in V star star, we can find some vector u which is norm of the form norm F times V such that F is equal to J. Therefore, J is surjective and hence by the definition of reflexivity, we had to show that V is reflexive. Reflexivity V is reflexive. And hence we are done. So I hope this proof was fine with everyone. If you have any doubt in any of the steps, please let me know. Okay, then let's move to the next question, probably the last one. Question number 5. Let V be a Banach space and phi from 0, 1 to V is a linear continuous function, then limit h tending to 0, 1 by h integration t to t plus h phi s ds is equal to phi t for every t in 0 to 1. So basically, if V is a Banach space and phi is a linear continuous function which has values in the Banach space, Banach value. So we can call it as a Banach valued linear functional, a linear function, continuous linear function. In that case, we have for every t in 0 to 1, phi t is equal to limit h tending to 0, 1 by h, and this integration t to t plus h phi s ds. Proof. Now to note this function, this as function of h, define vh for t in 0 to 1, we define vh is equal to 1 by h t to t plus h phi s ds. Now since phi is continuous, this implies for epsilon positive, there exists some h which depends on epsilon positive such that norm phi s minus phi t is less than epsilon whenever mod s minus t is less than h. Clearly, also since we are given just continuous, so this h will depend on the points s and t as well. Now, if f is in v star, suppose f be a linear functional in on defined on v. In that case, we have mod f phi s, because phi s, range of phi s is v and domain of f is v. So this f of phi at s is well defined, minus f phi t. Now this is less than equal to norm f, because f is a linear functional, times norm phi s minus phi t, which is less than epsilon times norm f whenever mod s minus t is less than h. Now let us see fvh minus fv, where this v is and v is phi. phi at t, na? T is fixed. Phi at t on this fixed t. And this is equal to mod f 1 by h integration t to t plus h phi s ds minus f at phi t. Now, by definition of the linear continuous map, Banach valued linear continuous map, you can see that this integration will come outside. So this is 1 by h integration t to t plus h f of phi s ds minus, I can write this as f phi t by h integration t to t plus h 1 ds. So I can take this 1 by h outside. This integration t to t plus h f phi s minus f phi t ds. Now this is less than equal to 1 by h integration t to t plus h mod f phi s minus f phi t ds. We have seen that this is strictly less than epsilon times norm f by h integration t to t plus h 1 ds whenever mod s minus t is strictly less than h. Now this integral is equal to h and this will get cancelled out. So this is epsilon times norm f. Now since this f and v star was arbitrary, therefore we have modulus f vh minus v is less than equal to norm f times epsilon for every f in v star. Now I claim that using this we get norm vh minus v tending to 0 as this is whenever for every h less than h epsilon. So this h, okay, I'll have to check why. Okay, so I'll check this how we are getting this h less than h epsilon. This is for every h less than h epsilon. So using this we can show that norm vh minus v should go to 0 as h tending to 0, because if suppose it doesn't happen, uh, suppose not, suppose not, in that case we have vh minus v greater than epsilon for some h less than h epsilon. Now since and by Hahn Banach theorem we can find some f in v star such that f at vh minus v is equal to norm of vh minus v and norm f is equal to 1, which will give modulus f vh minus v, which is equal to norm vh minus v strictly greater than epsilon. But for some h less than h epsilon, which is a contradiction to this star. I'll have to check why this for every h less than h epsilon is coming. Maybe we can discuss that in next class. So I hope this is fine. Is there any doubt in any of the previous questions we did today? Okay. Okay, then if you don't have any doubt, uh, we can finish it here. So we'll meet next Friday. From next week, we'll have classes on Friday only. Only for this week, I had some other important tasks, so that for that I had to prepone the class. Okay then. Thank you.
Nidhi,
Yes.
just one question. Could you
Yes.
give us some concrete examples of this map phi, which the last question which we discussed, from T to some Banach space? Maybe not right now, but yeah, if we could discuss in the next class.
Okay. So we need to find some function phi from some compact set to a Banach space,
Yeah, yeah,
and
yeah.
so that we can see this
Yeah,
limit is existing or not. Okay, I'll
I think
see if I could find. I'll surely tell you.
I think it's there in the lecture as well.
Okay.
Um,
So can you tell me so that I can just jump to that one?
No, I think it's in I guess week three.
Okay.
Vector valued integration. I think professor has discussed.
Okay. 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 Okay.
Yeah, yeah, yeah. So maybe, but I
Yeah.
really wonder what is like how it is being used in like a concrete way.
Okay. Okay. I'll try to see that lecture and then I'll explain you if I
Okay,
could
thank you
find
so
some example.
much.
Okay then. Thank you.